Electrical metallic tubing, commonly known as EMT, is generally not considered suitable for locations subject to severe physical damage. The roof of a strip mall with a flat roof is often classified as such a location. While rain-tight fittings are important for weather protection, they don't provide adequate mechanical protection. The National Electrical Code, or NEC, addresses raceway installations in areas where mechanical damage is likely. Let's consider NEC Section 358.12 Yon. This section states that in areas where mechanical damage is likely to occur, including parking garages, barns, stables, driveways, canopies, industrial or commercial buildings, or where corrosive vapors are present, raceways must be protected from damage by one of the following methods. Firstly, use of extra heavy wall rigid non-ferrous metal conduit. Secondly, use of Schedule 80 polyvinyl chloride, commonly known as PVC conduit. Thirdly, burial underground at least 6 inches below grade. Fourthly, lay within a concrete envelope not less than 2 inches thick. And fifthly, installation within a Schedule 40 PVC rigid non-ferrous metal or intermediate metal conduit or electrical metallic tubing raceway. Because the roof of a strip mall may be subjected to physical damage, such as from maintenance activities, dropped objects, or weather events, it is often necessary to use a more robust conduit system. Intermediate metal conduit, known as IMC, or rigid metal conduit, or RMC, are typically the preferred choices for these applications. These conduits offer greater resistance to physical damage compared to EMT. While EMT is suitable for many indoor applications and some protected outdoor locations, it lacks the necessary strength to withstand the rigors of a potentially damaging rooftop environment. It's important to always consult the latest edition of the NEC and local building codes to ensure compliance with all applicable regulations. The NEC provides specific guidelines for selecting and installing raceways in various environments, taking into account factors such as mechanical stress, corrosion, and temperature. Always refer to the relevant articles and sections of the code for detailed requirements. To summarize, EMT is generally not recommended for use on rooftops in areas where physical damage is likely. IMC or RMC provide better protection and are typically required by the NEC in such locations. Rain-tight fittings are important for weatherproofing, but they do not provide adequate mechanical protection. Always consult the NEC and local codes for specific requirements. The selection of appropriate conduit and fittings is crucial for ensuring the safety and reliability of electrical systems. Factors such as environmental conditions, potential for physical damage, and code compliance must be carefully considered. Always prioritize safety and adhere to industry best practices when designing and installing electrical systems. In the context of electrical installations, a feeder refers to a set of conductors that carry electrical power from the service equipment, such as the main distribution panel, to a subpole or a branch circuit panel. The feeder provides the electrical supply to these downstream panels, which then distribute power to individual circuits and loads. The size and type of conductors used for a feeder are determined by the amount of current the feeder is expected to carry, as well as factors such as voltage drop and the installation environment. The National Electrical Code, or NEC, provides guidelines for sizing feeders and selecting appropriate conductors and overcurrent protection devices. When a feeder is run in conduit, the conduit serves to protect the conductors from physical damage and environmental factors. The type of conduit used must be suitable for the installation environment, taking into account factors such as exposure to moisture, chemicals, and physical stress. For example, in locations where the conduit is subject to physical damage, such as in industrial settings or along roadways, rigid metal conduit or intermediate metal conduit may be required. In other locations, electrical metallic tubing, or EMT, or PVC conduit may be permitted. The NEC specifies the types of conduit that are permitted for various applications, as well as the requirements for supporting and securing the conduit. It is important to follow these requirements to ensure that the conduit system is properly installed and provides adequate protection for the conductors. The number and size of conductors that can be installed in a conduit are limited by the conduit's fill capacity. The NEC provides tables that specify the maximum number of conductors of a given size that can be installed in various sizes of conduit. These tables take into account the diameter of the conductors and the internal diameter of the conduit. It is important to adhere to these fill limits to prevent overheating of the conductors and to ensure that the conduit system is properly ventilated. When installing a feeder in conduit, it is also important to use the correct type of fittings. Fittings are used to connect sections of conduit together, to connect conduit to enclosures, and to provide access to the conductors for terminations and splices. The fittings must be compatible with the type of conduit being used and must be listed for the intended application. For example, when using rigid metal conduit, threaded fittings are typically used to provide a secure and watertight connection. When using EMT, compression fittings or set screw fittings may be used. The NEC specifies the types of fittings that are permitted for various applications, as well as the requirements for installing and securing the fittings. The size of the conduit used for a feeder is determined by the number and size of conductors being installed, as well as the conduit's fill capacity. The NEC provides tables that specify the minimum size of conduit required for various conductor combinations. These tables take into account the diameter of the conductors, the internal diameter of the conduit, and the directing factors that may apply due to the number of conductors in the conduit. It is important to select a conduit size that is large enough to accommodate the conductors and to provide adequate ventilation to prevent overheating. When running a feeder on the roof of a building, it is important to take into account the environmental conditions and the potential for physical damage. The NEC specifies the types of conduit that are permitted for rooftop installations, as well as the requirements for supporting and securing the conduit. In general, rigid metal conduit or intermediate metal conduit are preferred for rooftop installations due to their superior strength and resistance to physical damage. EMT may be permitted in some cases, but it must be properly supported and protected from damage. The conduit must also be installed in a manner that prevents water from entering the conduit system. This may require the use of watertight fittings and sealants. The NEC also specifies the minimum clearance requirements for conduit that is installed on rooftops. The conduit must be installed at a sufficient height above the roof surface to prevent damage from foot traffic, equipment, and other objects. The clearance requirements vary depending on the type of roof surface and the type of conduit being used. It is important to consult the NEC for specific clearance requirements. In addition to the NEC requirements, local building codes may also impose additional requirements for feeder installations. It is important to consult with local authorities to ensure that the installation complies with all applicable codes and regulations. A ground wire, also known as a grounding conductor, is an essential safety component in electrical systems. Its primary purpose is to provide a low impedance path for fault current to return to the source, typically the electrical panel or transformer, in the event of an electrical fault. This low impedance path helps to quickly trip the circuit breaker or blow the fuse, disconnecting the power and preventing electrical shock or fire hazards. The ground wire is typically connected to the metal enclosures of electrical equipment, such as appliances, lighting fixtures, and electrical panels. This ensures that if a fault occurs within the equipment, the fault current will flow through the ground wire back to the source, rather than through a person who might come into contact with the equipment. The size of the ground wire is determined by the size of the circuit conductors. The National Electrical Code, or NEC, provides tables that specify the minimum size of the ground wire required for various circuit sizes. It is important to use the correct size ground wire to ensure that it can safely carry the fault current without overheating or melting. The ground wire must be properly connected to the grounding system. This typically involves connecting the ground wire to a grounding electrode, such as a ground rod or a metal water pipe that is in direct contact with the earth. The grounding electrode provides a connection to the earth, which helps to dissipate fault current and maintain a stable voltage reference. The grounding system must be properly installed and maintained to ensure that it is effective in protecting against electrical shock and fire hazards. The NEC provides detailed requirements for grounding systems, including the types of grounding electrodes that are permitted, the methods for connecting the ground wire to the grounding electrode, and the requirements for testing and inspecting the grounding system. In addition to the equipment grounding conductor, which connects to the metal enclosures of electrical equipment, there is also a neutral conductor, which carries the normal and balanced current in a 3-wire circuit. The neutral conductor is typically grounded at the service entrance, but it is kept separate from the equipment grounding conductor throughout the rest of the electrical system. This separation helps to prevent unwanted current from flowing through the equipment grounding conductor, which could create a shock hazard. The NEC provides detailed requirements for the installation of neutral conductors, including the requirements for sizing, insulation, and termination. It is important to follow these requirements to ensure that the neutral conductor is properly installed and does not create a safety hazard. In summary, the ground wire is an essential safety component in electrical systems. It provides a low impedance path for fault current to return to the source, helping to quickly trip the circuit breaker or blow the fuse and prevent electrical shock or fire hazard. The ground wire must be properly sized, connected, and maintained to ensure that it is effective in protecting against electrical hazards. The NEC provides detailed requirements for grounding systems, and it is important to follow these requirements to ensure that the electrical system is safe and reliable. The size of the conduit is important for several reasons. Firstly, to ensure that there is enough space for the conductors to be installed without damaging them. Secondly, to allow for adequate heat dissipation from the conductors. And thirdly, to comply with the fill requirements of the National Electrical Code, or NEC. The NEC specifies the maximum percentage of the conduit's cross-sectional area that can be occupied by conductors. This is known as the conduit fill. The conduit fill requirements vary depending on the type of conduit, the type of conductors, and the number of conductors in the conduit. In general, the NEC allows for a maximum conduit fill of 40% for 3 or more conductors. This means that the total cross-sectional area of the conductors cannot exceed 40% of the conduit's internal cross-sectional area. The conduit fill requirements are intended to prevent overheating of the conductors and to ensure that the conductors can be easily pulled through the conduit during installation. If the conduit is overfilled, the conductors may be difficult to install and may be damaged during installation. Overheating can also occur if the conductors are packed too tightly together, which can reduce their ability to dissipate heat. The NEC provides tables that specify the maximum number of conductors of a given size that can be installed in various sizes of conduit. These tables take into account the conduit fill requirements and the directing factors that may apply due to the number of conductors in the conduit. It is important to consult these tables when selecting the size of conduit for an electrical installation. The size of the conductors is also an important factor in determining the size of the conduit. The NEC specifies the minimum size of conductors that can be used for various applications based on the amount of current the conductors are expected to carry. The size of the conductors is typically expressed in terms of their ampacity, which is the maximum amount of current that the conductors can safely carry without overheating. The NEC provides tables that specify the ampacity of various sizes of conductors based on the type of insulation and the installation conditions. It is important to select conductors that are large enough to carry the expected current without exceeding their ampacity. The directing factors can also affect the size of the conductors and the conduit. Directing factors are used to reduce the ampacity of conductors when they are installed in certain conditions, such as when they are installed in a hot environment or when they are bundled together with other conductors. The NEC provides tables that specify the directing factors that apply in various situations. It is important to take these directing factors into account when selecting the size of the conductors and the conduit. The type of conduit can also affect the size of the conduit. Different types of conduit have different internal diameters and different fill requirements. For example, rigid metal conduit, or RMC, typically has a larger internal diameter than electrical metallic tubing, or EMT, of the same size. This means that RMC can typically accommodate more conductors than EMT of the same size. The NEC provides tables that specify the internal diameters of various types of conduit. It is important to consult these tables when selecting the type and size of conduit for an electrical installation. The number of bends in the conduit can also affect the size of the conduit. The NEC limits the number of bends that are allowed in a conduit run between pull points. The pull points are the locations where the conductors can be pulled into the conduit. The NEC limits the number of bends to 360 degrees between pull points. This is to prevent the conductors from being damaged during installation. If the conduit run has more than 360 degrees of bends, it may be necessary to install a larger size of conduit or to install additional pull points. In summary, the size of the conduit is an important factor in electrical installations. The size of the conduit must be large enough to accommodate the conductors, to allow for adequate heat dissipation, and to comply with the fill requirements of the NEC. The size of the conductors, the dirting factors, the type of conduit, and the number of bends in the conduit can all affect the size of the conduit. It is important to consult the NEC and to follow industry best practices when selecting the size of conduit for an electrical installation.